Alright, so now that my slide deck is working, let's go ahead and get started. We're going to try this all over again. So hello everyone, my name is David Rock. I'm here at the University of Maryland in Baltimore, Maryland, and welcome back to Cytometry in R. So due to a little bug in the slide deck, I am re-recording this bonus walkthrough just to make sure to see how to go ahead and implement cleanup gates for signature retrieval. So, during weeks 12 through 14 of the Cytometry in R course, we primarily focused on how to work with raw spectral flow cytometry files. So, during week 12, we learned how to extract out and characterize fluorescent signatures that are present within our mixing controls, both single color and unstained. During week 13, we're going to learn how to compare these signatures with each other, which will allow us to predict how they will interact in the context of a full spectral flow cytometry panel. And then finally, in week 14, everything will come full circle when we take these fluorescent signatures that we have derived from our mixing controls and use them to unmix full stain samples. So, due to the Cytometry in R's course use of GitHub, we are not able to include the full-size FCS files due to their individual file size sharing constraints. So the datasets that are used during week 12 through 14 had to be downsampled to get around this particular issue. However, working with complete datasets can provide additional insight, as well as more closely replicate the experience of working with our own datasets. So consequently, this walkthrough contains the steps that are needed to both retrieve as well as process the original FCS files that were used from the import repository in the previous walkthrough. So continuing where we had left off at the import walkthrough, we're going to proceed to assemble gating sets for single color and mixing controls, both for beads and for cells, as well as an additional gating set for our unstained unmixing controls. These will include the cleanup gates to ensure that we are only gating on events that are actually interested in. For a typical workflow, these would then be saved to their own gating set.gs object within our local environments as an intermediate, which would allow us to quickly return them subsequently tomorrow, next week, next month, whenever we're actually ready to work with the gating set again. So it is from those intermediates that were generated as part of this walkthrough that the final data sets for the Cytometry in R's week 12 to 14 material were retrieved at the very last cleanup gate using the downsampling function that we wrote back during week 10. So, in the previous walkthrough, we downloaded the original FCS files for the SDY3080 dataset from import, focusing in on our first two experiments, ILT_00, as well as ILT_01. We're going to proceed to save these within the data folder in their own respective subfolders, based on the type of FCS file, unmixing control cells versus beads, or an unstained cell control, or a full stain sample. And this is an example of what that organization scheme looked like. In this case, I was saving underneath the SDY3080 folder, I had a data folder, and then I had yet another SDY3080 folder underneath of there. But then you can see in this example here, we have the full stain sample subfolder, a single color control cell folder, an unstained cell reference folder, and then a single color bead reference folder as well. So, now that we have all these individual FCS files that we have retrieved from import within their own subfolders, we need to go ahead and load them into a gating set object for use with the Flow Workspace package, as well as implement some basic cleanup gates using the FlowGate package. So we will then at that point check to make sure the gates are applied correctly across the board for the individual specimens, ensuring that everything is in order before we save these out as intermediate.gs objects, so that we're able to quickly retrieve them if we need them in the future. So, before getting started, it is worthwhile, especially if you're working within your own project folder within Positron and are actively using version control, to make sure to update your .gitignore file before proceeding so that you avoid accidentally committing these FCS files that are going to be very large files to your GitHub. The main reason for this is the largest of the full stain samples, for example, is about 300 megabytes, so well and truly above the GitHub file size limit. So if you're able to avoid accidentally including these in your commit history, you can avoid yourself a lot of pain as you go forward with the analysis. And if you have created a Git repository when you initiated your project folder, you should already find a .gitignore file in the primary left sidebar. So the way a git ignore file is used is basically it designates specific files or particular folders that should never be tracked with version control using git. This is often used to basically avoid sending large files, any files that contain sensitive information, like passwords, that you would basically want to remain strictly on your local computer and not end up on a remote repository. So in my case for this particular project, you can see I have a git ignore folder, a git ignore file that you can see within the primary left sidebar. And if I go ahead and click on it, you're going to get it popping up in the middle console. So when opening a .git ignore file for the first time, there's typically only a couple items that are going to appear being listed. Most of these being like background, positron, or Corto processes. And for this particular walkthrough, all my FCS files are currently being stored under the subfolder data under its respective SDY3080 subfolder. So if I want to ignore all subfolders below that, I could just designate the SDY3080 folder in my .git ignore file so that everything that is contained below just gets ignored and not included in version control. Subsequently, anything that is in that folder doesn't get tracked, and I don't have it accidentally end up in my commit. Likewise, for those, as we assemble our gating sets together and then store them as intermediate.gs folders, I don't want these being included because they are also going to be substantially large. So basically, if I want to be able to exclude all .gs folders, regardless of where they are located at, I can just place the line .gs, between quotation marks, star.gs in the .git ignore file, just to make sure all those GS intermediate folders and all their contents are also not committed to version control. So what this looks like in practice, as you can see, if I'm trying to just find any .gs folder and exclude it, I'm just going to do star.gs. And then for a specific folder, I'm just specifying data SDY3080. And as you can see, data SDY3080 now becomes grayed out across the board, similar to what I have for the Corto file, which is also being specified in this .git ignore. Then at that point, I can save, commit changes to my git ignore so that it's reflected and remembered next time I actually am using it. So, as you may recall, back during week 8, we first learned how to use the Flowgate and the OpenCyto package to implement both manual and automated gates. So, while using Flowgate's Shiny app is quite helpful, we struggled with limited options in terms of if the gate being applied based on individual specimens was not correctly applied across the board for all the specimens, we would then need to go back in, delete the entire gate, and try again by drawing a more liberal gate for what we had. So, since the Flowgate package is open source, what I ended up doing over the little summer break was writing several additional functions that basically allow us to adjust the gate placement on a per individual basis while leaving that same gate intact and in place for the other specimens. So I submitted these changes to Andrew White, who's the package maintainer, and he ended up merging them into the Flowgate's developmental branch. So, if you may remember, Flowgate is a bioconductor package, and bioconductor does twice yearly release cycles, which means they will roll in and actually be in the bioconductor install version probably in the next major release, which is going to be around October. So, in the meanwhile, probably the easiest way to install a Flowgate that also contains these changes would be from the GitHub repository so that you're able to use these new functions. As always, the easiest way to do this is first you would need to remove the existing Flowgate package from your computer, close and reopen Positron, and then proceed to install the new version. Now, some of those of you who are on the discussion forum for the Cytometry and R course may have noticed there's been a few issues that were encountered after the release of week 12 related to this particular step. And the reason for this is there's been a change at the bioconductor level in how the transform function is applied, and these changes were rolled out to Flow Core, Flow Workspace, ggCyto behind the scenes, but have not yet been updated within the Flowgate package. So consequently, if you're reinstalling Flowgate at the time of this recording, which is July of 2026, this may not be applicable for those of you who are watching this in the future. What you need to do is, as you uninstall and then reinstall Flowgate, it's going to give you that pop-up of, do you want to update all these packages? And it's going to give you a list of CRAN packages and then a list of bioconductor packages. But you'll also notice it's going to try to update the ggCyto package based on a git commit. Basically, what you need to do is either not update any of the packages across the board, or if you're updating a package for the time being, just update the CRAN packages select that option, but not update the bioconductor or the GitHub packages. That will give you the working version of both the Flowgate package today, but then also the Lucernica package tomorrow when you need to reinstall it. And then that gives us enough time as the course to go and actually write the changes we need to do to Flowgate to handle the new transform behavior for the generics within bioconductor. So a workaround, just like we've encountered a couple times in this course, when suppin changes upstream, ggcyto and Flowgate tend to be the things that get impacted the most. So we need to do this little bit of navigation today just to make sure we get working versions that we can adjust our gates for. So what this looks like in practice, we can then use the remove.packages function to go ahead and remove Flowgate. And then after reopening positron, we can go ahead and use either the remotes package or the pack package to go ahead and install from GitHub. In this case, the Git account is nkinstinct, and then the repo is going to be /Flowgate. So that will bring in the one that you're trying to get for this particular walkthrough. And then if everything is successful, that one that has those ggplot2, ggcyto bugs fixes is going to be the version 1.13.1. So if you want to check which version is currently installed on your computer, you can run package version and it will pop up nonetheless. Alright, so at that point, we need to go ahead and start our initial setup. So at this point, the workflow falls very much into the routine that should be familiar to those of you who have gotten through the first section of the course. As always, we'll begin by loading the required R packages that we need via the library call. In this case, we're going to go ahead and load Flow Workspace, Flowgate, dplyr, and the per package. Next up, since we are relying on the downsampling function that was created as part of week 10 of the course, we need to grab that R folder that we've been using to store the intermediate.r files and just be able to source it to bring all those contents into our local environment. So the way we've been doing it so far in the course is within our working directory, we have that R folder with all our little individual created functions. We list those individual .r files that are present under an object called myfunctions. And then we're iterating through each of those particular file paths and passing them to source, which is just basically activating those functions and creating them within our working environment. So once that's done, we just need to designate both the input file path, i.e. where our respective FCS files are being stored, as well as the output file path, where we want any intermediate objects stored to. So for the organization schema we have had this walkthrough, this would look something along these lines. Namely, we are pointing at our STY3080 folder, which is under that data folder, where all the little individual subfolders for single color beads, single color cells are stored. And then for an output location where we want to save those intermediate.gs folders, we can just put it within an outputs folder that's directly below our working environment. So with those initial file paths set up, we can then proceed to identify individual subfolders that are located underneath storage location, which will correspond to the individual reference control type. So once again, we can just go ahead and list .files for that particular file path to identify the folders that are present. As you can see, we got the full stained, we got the single color beads, we got the single color cells, and we got the unstained cells. Then at that point, I'm just going to go ahead and designate them based on name instead of having to remember which index is which. So I'm just going to head and write them out to their own objects or variables within my working environment. And then at that point, I want to take those file paths and go ahead and load in each of the respective FCS files into their own gating set based on their particular unmixing control type, just so they're a little bit easier to work with across the board. So let's start up with just the bead single color gating set on target our bead single colors. So once again, we are looking at this particular file path denoting our bead single color folder. We're listing the files that are contained within that match the pattern.fcs, retrieving our flow cytometry files. These are now present within bead_files within our working environment. Then using the flow workspace packages, load cytoset from FCS function, we can load those into a cytoset object, which we can then wrap into a gating set using the gating set function. And then that one's assembled and ready to go. If you check it, you can see all the bead single color controls are now present. We can then follow this up for the exact same steps, but this time targeting our cell single colors. And what we're going to do is same thing, just pointing at the cell single color file path, load them in and identify all the FCS files, proceed to load them into their own little cytoset, and then wrap them into a gating set object that we are able to interact with a little bit easier in R. Once again, if we check the P data, we can see all these individual files are now present and are now utilizable across the board. And last but not least, we can repeat these steps for our unstained gating set for our unstained unmixing controls. So once again, pointing at that particular file path denoting our cell unstained sample folder. Once we identify these FCS files, load them into a cytoset, and then load them into a gating set. And as we check, we can see we have 12 samples denoting unmixing controls for unstains. These, in the case of the SDY3080 gating set, this is going to be specimen-specific as well as stimulation-specific controls for unstained. So, in the next couple walkthroughs, we are working with basically raw FCS files. So you may be wondering, based on what we've done previously, if we're going to need to transform these files. Since as we're going to be extracting out the single color and autofluorescence signatures, which will rely on the raw values, our first inclination may be to correctly assume that we do not need to transform, since this may overall impact or distort the overall signature that we end up retrieving. So, however, we first need to go ahead and gate on the cells that are positive for a given marker before we can extract out the signature values for those cells that are contained within the gate. Since flow cytometry data for the fluorophores is typically visualized on a bi-exponential or a logarithmic scale, this doesn't quite work out well in practice if we leave these values untransformed and being viewed linearly. So we need to first transform our data sets, but we need to remember that at the time of extracting out the values for use in the signatures, we need to provide the argument inverse.transform is equal to true, so that those transformations get reversed and we're left with just the raw data. So how are we going to do this? So similar to what we've been seeing since week 7, if we take the column names of our particular gating set, we can then retrieve those parameters that are present within. And then at that point, we just need to find our fluorescent detectors, not anything that's going to be linear. So we need to exclude things like forward scatter, side scatter, and time. So remember, the stringers package's structure detect can check those column names, and if it finds this matching pattern, it will return a value of true. At that point, that's not something we want to keep, it's something we want to exclude, so we can add that little exclamation sign up front, which will basically flip it. So anything that comes back as false will be flipped to being true, and those will be retained, and vice versa, anything that's true for matching these particular patterns is going to get flipped, and it's going to be excluded from the final one. So at that point, we're left with a vector of just our fluorophore parameters, which we're then able to use for the transformation. And for this particular gating set, it ended up having 5.62 for positive decades, a width basis of -1000. I visualized this with ggCyto just to make sure it was actually appropriate for this gating set. If you're following along at home using your own gating set, your own instrument settings may be different, so please go ahead and double check this, just because the main issues with your data oftentimes are a misapplied transformation. And then once that's done, you create your transformer list on the basis of those isolated parameters, giving them these particular values, and then you just go ahead and transform your gating set across the board, in this case for beads. And then at that point, you can repeat a similar process when it comes to our cell single color controls, going across the board. And finally, but not least, those unstained cells to also have transformations being applied. So, at this point, we need to go ahead and implement some initial gating sets. We need to also add some initial gates through the use of the flowgate package. And the easiest way to do this, as we saw back during week 8, is going to be through an iteration table approach. This way, for beads, for example, we would then consist of creating a table that will draw for both the scatter and the singlet gate, kind of similar to what we've encountered in the past. However, for cells, given that quite a few of our controls are actually not peripheral blood mononuclear cells, but actual core blood mononuclear cells, we're going to need to add an additional cleanup gate, namely to get rid of any residual red blood cells or pre-red blood cells that might be present after the freeze-thaw cycle. So as you can see, this is a little bit more complicated on the gating template. To get rid of those RBCs, we're taking advantage of the difference as far as the absorbance of the hemoglobin for the violet versus the blue laser. So we're putting side scatter A versus side scatter blue to exclude out the non-RBCs, to include only non-RBCs, and then we can draw a scatter gate afterwards. So let's see how this applying the gating table approach works with flow gate. So once again, we're going to be using the gsapply gating strategy function when we're actually iterating. So basically, we're running that function on our gating set of interest and applying our gating template of interest. And as we hit run, the little shiny app in positron is going to open up on the lower right secondary sidebar. If it's kind of squished, you can just go ahead and grab that little gray line and drag it over until you can see a full stain view. And then at that point, you're able to draw gates based on your different preferences. So in this case, I'm going to go ahead and select the polygon gate, and I'm going to target these beads that are in pretty good shape. So as I'm doing that, I get to this situation. If I'm happy with my gate, I can just go ahead and select done. And then this same gate is going to be applied to all the bead samples that are present within that gating set. If I mess up, I can just go ahead and hit reset and then try again by drawing a new gate until I'm happy with it, and then I can select done. And then at that point, it's just going to iterate into your next gate that needs to be created. In this case, it's going to be the singlet gate. I can draw a singlet gate around what I assume are singlet beads. And then if I'm happy with it, select done and apply it to all the different specimens in that particular gating set. Now, we can use that newly created function that was added to FlowGate over the summer, a GSApplyGate check, to basically iterate through each specimen within our gating set for a particular gate and actually apply those controls. So what this is going to look like is we're going to first run it on the bead gating set and specify that very first gate we created for scatter, and it's going to pop up the very first specimen. And the previously created gate will be seen within the little red lines as far as what we see. If we're happy with this, we can go ahead and select done. If we are not happy with it and we want to redraw it, we would then select the polygon, draw a new gate, which will show up as the little black lines, and that would be all we would need to do. So this is what it looks like in this case. If you are saying this guy is a little bit too broad, we could just go ahead and select polygon, draw around again, and then what we'll end up visualizing will be something similar to this one. If you're happy with it, select done. If you want to try for a redraw again, you can do a reset. And then ultimately, after you iterate through all the different specimens and are happy with the scatter gate for those beads, you can repeat the same process for your singlets. So this is what this is going to look like. You draw your gate initially around the singlets. If it's happy, you're going to be good, so you can just select done. If, however, you're missing part of your singlet gate and you want to modify it, select the according gate type, draw a new gate, and then at that point, select done, as you can see in this case here. Additionally, there's a new function which will allow you to take a particular your gating objects that you've created for one particular specimen, and convert them over to basically the gating template.csv layout that's expected for the OpenCyto template. That will therefore allow you to be able to apply those exact same gates across the board for all specimens, regardless if it was in today's gating set or something you load in next month or later in the year. So at this point, the two new functions that are being integrated within Flow Workspace allow you to both modify existing gates on a per individual basis, which puts you a lot similar to the commercial software in terms of your capabilities, but then also puts you half a step towards OpenCyto in terms of you can draw gates that you want applied across the board in a more automated fashion, and then have OpenCyto do those gate applications for you without having to do the little shiny launch. So what this is going to look like for GS to OpenCyto function: you provided your gating set, the sample that you want to be used, and then the file name and out path you want to save the CSV file to. And last but not least, having put all that effort to create the gates of your gating set and make sure they're correct, you should save this as an intermediate folder just so you're able to load them in tomorrow, next week, next month, whatever the case may be, without having to go through all the trouble of recreating all those steps. So this is a Flow Workspace package function, namely save_gs. You need to specify your output location, the new name of that folder, which I'll always just denote .gs, so I'm always constantly knowing what's being happening. And then you pass the gating set and your save location too, and it will go ahead and create that folder and place all the internal contents below. And then once that gating set is being created for the beads, we're now done with those single colors. We can then repeat the workflow when it comes to the cell single color and mixing controls. So we can do that exact same strategy. In this case, we're just applying the cell gating template to being actually applied to the cell single color gating set. And once again, creating that initial folder, that initial gate based off of the singlets. And when we're happy with it, we can go ahead and select done. We can do that little RBC exclusion gate off of the side scatter A and side scatter blue, and then select done. And then for your cell single color controls, this is going to be a little bit variable because it's a mix of both cord and PBMC, cord blood and peripheral blood mononuclear cells, as well as stimulated and non-stimulated. So this is where I expect to see most of the variability. But for now, let's just draw a good general gate around what's the lymphocyte population and go ahead and select done. So each of these gates that we drew on a per individual basis will now, on this basis of this individual, will be applied across the board for all the specimens within our gating set. And then at that point, we just need to run gs apply gate check on each individual gate for that gating set, iterate through all the different specimens, apply any corrections that need to be applied, save those individually so we don't have to worry about them in the future. So once again, similar to what we did for beads, we can check off the singlets gate. You can see this is an example where we modified the singlets for this specimen so it's not cutting quite as close. And then at that point, you can repeat for the RBCs, so checking for RBCs. And then last but not least, we expect most of the variability in the gate placements to be for scatter, just because of all the variation we have internal. So if we run and check on a scatter gate, you can see this is one that ended up being applied for a PBMC for that first initial specimen, but this is visualizing it with cord blood. You'll see it's cutting into this RBC/dead and dying cell population, which may be looking quite different in terms of the signature. So we're definitely going to want to redraw it to make it a little bit more narrow and concise on just the same population that we're interested in. And then once this is done, we can select Done to update the gate accordingly for this particular specimen. And then at that point, if you think about it, there's a couple single color controls for cells that are not going to be typically placed on your PBMCs when it comes time to extract the signature. A good example is the dump channel Pacific Blue CD14, which should actually be placed on the monocytes if we're adhering to the gating based on the as bright or brighter rule. And then similar story for our zombie NIR controls. They're not going to be likely on a healthy forward scatter, side scatter population of lymphocytes. They're going to be more of those rapidly downsizing size cells that have the as bright or brighter signal. So we may want to adjust those scatter positions individually right now, just so we don't have to worry about them later next walkthrough when it comes time to finding the brightest signal. So, to save our eyesight and sanity, remember there's up to 33 single colors somewhere in this gating set. We could check P data and find them individually, or we can do a little bit of an intermediate modification and just go ahead and extract our P data and mutate on a new column using the dplyr package and its row number function just to quickly identify what the row number is. So this is what that code would look like in practice. We grab our metadata, that data frame, we pass it through the pipe to mutate. It creates this new row column, which identifies using row underscore number. As you can see, this is not being appended back. This is just being outputted to our console window. It's not actually saved as an environmental variable. And then at that point, I can see that my two zombie controls are at position value 31 and 32. And I can see my dump channel CD14 Pacific Blues at index value 24. So these would be the values I would use to actually go and modify those individual gates using the gs apply gate check function. So as you can see, targeting that one, we need to adjust from where it's on lymphocytes over to monocytes so it accurately is able to grab the bright CD14 signal. Once again, I'm just going to modify the scatter gate. And instead of being where it is here, which doesn't going to have any signal for CD14 for the most part, I'm going to adjust it and place it on the monocyte population. And then I can repeat the same process for both of the zombies, which are going to be based on cord and activated PBMCs. As you can see, the cord, dead and dying, are going to be more likely back here in this corner, so I can adjust the population gate over there. And same thing for the PMA unmixing activated. You can see they're starting to stretch over. More of the dead cells in that PMA condition are likely to be over here. And then at that point, we can just go ahead and save that GS to OpenCyto. So we have that gating template from the OpenCyto package if we decide we want to implement it. So we just designate which specimen we want from the gating set and save it out as its own template for later use. And last but not least, we have gone ahead, put all this effort in to check and validate those gates, so we should save it as its own intermediate.gs folder. So we're specifying our output location, giving it a new unique name, and the .gs notification so that we know exactly what it is, and then pass it to save.gs so it can write that folder and then put all the contents of our gating set underneath of it. And very much last but not least, we have our unstained cell controls for our SDY3080 dataset. These were consisted of cord blood specimens. For every individual specimen, we had some unstained, and both for control in the PMA conditions, just in case there was variation in autofluorescence based on these ones, which may or may have not been a tad bit overkill in hindsight, but we'll see what this looks like in the next couple weeks. So the process for setting up those initial gates is pretty much identical for the single color cell controls. Main adjustments that you're going to need to do is just the scatter gate, because some of these are PBMCs, some of these are CBMCs. So you apply your initial gates using that rolling cell gating table. You draw the gate based off of that first specimen. That's applied across the board to everybody. Same thing for scatter. And then at that point, your responsibility is just checking each of them individually via GS apply gate check, checking each individual gate so you can see for singlets being applied across the board, for non-RBCs being applied across the board, and then finally for scatter being applied across the board. And then we can save those same kind of intermediates. We can save the open Cyto template, and then save this already assembled gating set for cell unstains to its own respective .gs folder, so we can load it in whenever we need it. And then finally, at this point, with all those cleanup gates being properly applied to the tree gating sets, I ended up taking that particular save point and passing it to our downsampling function we created back during week 10 to basically save out 5,000 beads and 10,000 cells respectively for each of the controls as their new FCS files, which are now the dataset being used for the week 12 to week 14 in the Cytometry and R course. So the code of how to do this, in case you're trying to do this for your own projects, is also included below. Namely, I'm designating a new folder. I'm also using programmatically to see if the folder doesn't already exist. Use the dir.create function to go ahead and create it. Then I'm specifying the individual control folders, in this case for single color beads. If that is already an existing folder underneath class downsample, it would create it accordingly. And then basically we're iterating through our gating set, passing it to the downsampling function, retrieving based on a singlet gate, in this case 5,000 beads, and writing them out as their own FCS file. And then this process would be repeated similarly for our single cell controls. In this case, it would create their own specific folder. It's grabbing off of the scatter, which is that terminal gate, grabbing 10,000 cells, so it's pretty cleaned up across the board. And last but not least, the unstained samples, similar thing, scatter gate, and up to 10,000 events across the board, being saved as their own FCS files. So, in the course of this walkthrough, we have loaded in our mixing controls, both single color and unstained, into the respective gating sets. We've transformed them, and we applied initial gates. We then used the new flow gate functions to double check and validate that these gates placements were correctly applied across the board for every individual, modifying accordingly to make sure we have good quality data that ended up being saved into our intermediate.gs folders. Hopefully, all this effort we put in pays off in the future analysis, as it limits the ability of antibody aggregates, debris, doublets, and dead cells from ultimately impacting the signatures that we're interested in for our cells of interest when it comes time to unmixing. So in the next portion of the walkthrough that we'll go through tomorrow, we're going to orchestrate the creation of additional individual gates for every single color in our panel on top of these initial gates that we have saved into our intermediate.gs folders. This will then in turn allow us to derive the single color unmixing matrices that we need to do to extract out the normalized fluorescent signatures, which would then be used later on for a mixing of the full stain samples. And with that, that's all I have with you guys today. I hope the slide that did actually work for the second half. I'll see about modifying the actual video to not include the first half, which is just narration without actually any change of slides. And with that, I hope you have a good day, and I will